In this video, we're going to take a look at the derivative of inverse functions. But before we start looking at the derivative, we're going to do a quick recap of what an inverse function is. So I'm starting with a definition that should be a review, that we say that f inverse is the inverse of f, and our notation is by putting a little to the -1 up here on our f function, if, when we take the composition f inverse composed with f, we get out x again. And conversely, if f of f inverse also has to be equal to x. Well, what does all that notation mean? That's sort of a messy thing. Let's look at a concrete example, and it'll make a lot more sense. So, for example, if I have some function f of x given by x cubed plus 2, we can recall that the inverse of this function algebraically is going to be found by undoing each piece of this function. So, for example, I see that my inverse in this case, I'm going to have to subtract 2 and then take the cube root. Or in other words, I can set this equal to y, for example, and say that y is equal to x cubed plus 2. If I want to know what is the inverse, it's the undoing function. To undo this, I'm going to have to undo each operation in order. I get y minus 2 is equal to x cubed, and now I'm going to take the cube root of each side, or I can think of raising each side to the 1/3 power. Those are equivalent statements. Raising to the 1/3 power is the same thing as taking the cube root, and that means that undoing this, I see that x is equal to y minus 2 all raised to the 1/3 power. So this really is my inverse function. It's just a messy way to write it. Typically with standard notation, instead of having my input be a y and my output be an x, I'm going to flip my inputs and outputs to say that, aha, that means that my inverse function, I'm going to plug in my when I flip my inputs and outputs, I end up with an inverse function where my input is now an x, and I get x minus 2 to the 1/3. Well, why does this make sense? Let's go back to the original definition and take the composition of f inverse of f to verify at least one direction of this inverse function. So we're going to verify that f inverse of f of x is actually equal to x. So what is my f inverse function? My f inverse function is this function, and I'm going to plug into it my f of x function. So in this case, f inverse of f of x means that everywhere I see an x in my f inverse function, I'm going to plug in this function instead. So my f inverse function looks like x minus 2, but instead of x, I'm going to put in my original function, which is x cubed plus 2 minus 2 all to the 1/3. So in here is my f function. My f of x is right in here, and I'm plugging this chunk into my inverse function, which is the outer function. So what happens algebraically? I see I get x cubed plus 2 minus 2, and those cancel one another, and I'm left with x cubed on the inside of the parentheses, all raised to the 1/3 power. Well, x cubed to the 1/3 gives me out x again. So indeed, I see that when I take my inverse function and plug in my original function, I get out exactly what I started. I can also see this as an example with a number. For example, let's consider what is f of 2. Well, that's going to be 2 to the 3rd plus 2, which is equal to 2 cubed is 8 plus 2 is 10. For our inverse function, I take the output and plug it in, and hopefully I'll get what I started with. So let's consider what is f inverse of 10. I'm going to plug 10 into my inverse function, which in this case is 10 minus 2, minus 2 all raised to the 1/3 power. 10 minus 2 is 8 to the 1/3, which is the same thing as the cube root of 8. What's the cube root of 8? What times what equals 8? That's 2. So this is verifying for one particular point that I plug 2 into my function and get out 10. and I plug the output 10 into my inverse function, and I get out 2 again. Why is this interesting? This is interesting because when we analyze graphically what's going on, here's just some generic graph of inverses. We just decided that if our original function looks something like this, what happens when we take the inverse of our function? Well, it's the same thing as flip-flopping our outputs and inputs, meaning if I plug in a point A into my function f, I get out the point f of a. Maybe we'll call this point b, just for clarity's sake. Well, what does the inverse function do? The inverse function is such that if I start with a point b in my inverse function, I'll write my inverse function values in green. If I start with b, these are the same height. This height b becomes a length b, and I plug it into my inverse function, I better get out a point a. And that's true for every point on this graph. When I plug in this point, I get out a height of 0. So if I start with a height of 0, I better get out something at that height as well. It means that my inverse function is going to exactly flip-flops the inputs and outputs, which is the same thing as reflecting it along the line y equals x. Graphically, that's what an inverse looks like, and I'll summarize that in language. In language, I just said inverse functions switch inputs and outputs. Of the original function. So inverse functions, maybe f inverse, my inverse function, switches the inputs and outputs of our function f. And what does that mean graphically? That means f inverse is the reflection of f along the line y equals x. So why is this interesting? Whoops, along the line